Since we've been looking at estimating the values of functions with these Taylor polynomials, we should probably talk about the remainder, how far off they actually are. If I let Pn be the Taylor polynomial of order n for my function f, then we can define our remainder, Rn of x, to be equal to f of x minus Pn of x. So the n's are the degree of the Taylor polynomial that we're using, and x is the point that we're actually estimating. And we can actually write this remainder term very nicely using something known as Taylor's theorem. Taylor's theorem assumes that we have a function with continuous derivatives up to the n plus first derivative on some open interval I containing our center A. Then the remainder is going to be Rn of x is the nth derivative at c over n plus 1 factorial times x minus a to the n plus 1, where c is just some point between x and a. So it doesn't give us exactly what that value of c is. All we know is that it's somewhere between x and a. So since we can't say exactly what value that c is, we want to be able to estimate exactly what the remainder is. And we can do that. So we can estimate the remainder by supposing there's this number m, such that the absolute value of the nth derivative of c is less than or equal to m for all c between a and x, inclusive. So we do include a and x. Then the absolute value of Rn of x, which is defined as the absolute value of f of x minus Pn of x, is less than or equal to this number m times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. So let's see if we can use this. So I want to find a bound for the absolute value of the remainder for Taylor polynomials of f of x equal to sine of x centered at 0. So I'm not giving a specific value for n. I want to try to find a general formula. Well, we know that all of the derivatives of sine are either going to be plus or minus sine or plus or minus cosine. And we're centering them at 0. So sine of 0 is 0, and cosine of 0 is 1. So all of these derivatives are either going to be 0, 1, or negative 1. So I know the absolute value of Rn is less than or equal to m times x minus a to the n plus 1 over n plus 1 factorial. In this case, we're centered at 0, so a is going to be 0. And my m value is going to be 1, since, like I said, this entire function is bounded between 1 and negative 1. So I have that the absolute value of Rn is always going to be less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. So if you know what value you want to estimate, x, and what polynomial you want to use, that would be n, you can figure out exactly where the remainder is, or at least the absolute value of the remainder. Let's do one that's a little bit more concrete and a little less general. This time I want to estimate the error in approximating e to the 0.4 using P6 of x, so I'm going to use my 6th degree Taylor polynomial, for f of x equal to e to the x centered at 0. We need to start by finding a bound for all of my derivatives. Since we know the derivative of e to the x is e to the x, I'm trying to find the bound for just e to the x. So what I'm really looking for, absolute value of e to the c to be less than or equal to m, and c needs to be between my center 0 and the number I'm approximating 0.4. We know that e to the x is an increasing function, so e to the 0.4 is definitely going to be the largest possible value for this on this interval. However, we're also assuming that we don't actually know the value for 0.4. So we need to try to find a good bound for it. We don't want to get something too high, because then it's going to really overestimate how much error I have. So we want to try to find a conservative bound. And I'm going to use m equal to 2 as a conservative bound. It's not going to be the perfect bound, but it will work. This number is definitely less than 2. I then have the absolute value of R6, since n is equal to 6, of 0.4, which is the value I'm estimating, has to be equal to the value for m, which is 2. We then multiply by the absolute value of x minus a to the n plus 1. X is 0.4 and a is 0, so the absolute value of 0.4 minus 0 is just 0.4. And we need to raise it to the n plus 1 power, so the 7th power. We then divide by n plus 1 factorial, which is 7 factorial, which gives us approximately 0.000007. So our error is going to be less than this. We have less than 7 times 10 to the negative 7th error.